Hello and welcome again to Clinical Optics Made Easy. Today we're going to have more fun with lenses. I'm once again your intrepid host, M.N. Wiggins. And on today's feature, you're going to be seeing things such as thick lenses, principal planes, cardinal points, mystery pastries, how to spell long words, and the lost rules of Kestenbaum. Once again, everything that I'm talking about is coming out of this book right here. You can read any optics book you want to, but as always, please read something that gives you lots of problems to work. Perhaps like this one, tests that you can work through and see kind of where you are. The important thing is that you have a book that you can read and can get through and that speaks to you. If this is the one that you want, there's a QR code there. You can go to davisstreetpublishing.com and find it in lots of different locations. So let's get started here. We have an image 50 centimeters to the left of a +6 lens and forms an image where. This is basically from our very first lecture where we talked about the simple lens formula. And as you hopefully know by now, that means that U is going to be a -2. We have D as +6. That means that V must be a +4. And 100 divided by 4 is 25 centimeters to the right of a lens. Notice the disclaimer at the bottom. It's kind of in small print there, but it says, assumes an infinitely thin lens. What does that mean, an infinitely thin lens? Well, Hemingway said that greater understanding sometimes requires the omission of details. If you've never read A Farewell to Arms, it's an excellent book, but it says that sometimes we explain things in a simplistic form so that we get the idea, and you don't really need all the details to really get the concept. And that's what we've done so far in these lecture series. But today, we're going to talk about those details so that you kind of have an appreciation for what we've simplified. So this is how, in reality, the problem would be given to you rather than in the simplified form that we've been using. An object 50 centimeters to the left of a 3 centimeter thick lens forms an image where and has the following properties, and it tells you the power on the front surface, power on the back, and it tells you the principal plane is located here and the principal back plane is located there, and it gives you an RI. Now you've got 100 questions. What the heck is a principal plane? How do we plug in thickness? Why would we want to? What's the power of the lens? Why does refractive index matter here? So we've got a lot of ground to cover to kind of get through these definitions. And again, this lecture today is a concept lecture just to give you an appreciation for assumptions that we've made. And this will hopefully make sense to you as we go through. So front and back principal planes, they define the position of an object in an image such that the mag equals 1. Let me explain that a little further. Let's say I have an object 33 centimeters from a +6 lens, and that forms an image 33 centimeters to the right. That means that the magnification is going to be 1 based on the simple lens formula, and magnification is U over V. That defines a principal plane. Here it is in a diagrammatic form. The object and the image are the same size, and U over V therefore equals 1. That defines principal planes. Now the one over here on the left is going to be the front principal plane. It's in front of the lens. We're going to call that P1. And then we have a back principal plane, which we will very intelligently somehow, for some reason, call P2. So let's look at this in more detail. But before we do, I'd like you to go back and remember what primary and secondary focal points are. So here is a primary focal point. It starts out as a point, it diverges, it hits a lens, and then it emerges parallel. So a primary focal point starts at a point, and after it hits the lens, the rays come out parallel. That is a primary focal point. A secondary focal point, the rays start out parallel, hit the lens, and then come to a point. This is what we use to burn ants on a sidewalk. Once again, you can see a little disclaimer, tiny. It's very small down there, but you can see it. It says this assumes an infinitely thin lens. So more disclaimers. What's that all about? Well, if I were to diagram all of these points that we're talking about, it would look like this crazy looking diagram right here. But let's just start it and walk through it. So over here on the left, I have my object, this green arrow. And so I have a line, this first highest line here that's diagonally going off of this green arrow. It's going through my primary focal point, the PF right there. as it goes down, it hits P1, my front principal plane, and that's where it changes direction and it emerges parallel. Because when things hit the primary focal point, they hit the lens and go parallel. But in reality, it's not that it's just hitting the lens, it's hitting the primary principal plane or the front principal plane or P1, whatever you want to call it. That's where it changes direction. Now, let's go back to the object. See that parallel line that's coming off of it? Here I have a parallel ray. When it hits the back principal plane, P2, it's now going to change direction and go through the secondary focal point, the one that burns the ants. So it's fulfilling that definition of a secondary focal point, starting out parallel and then changing direction. But again, we were giving you a simplified version where somewhere in the middle of the lens it kind of changes direction, but the actual exact spot where that change in direction occurs is a principal plane. So the primary focal point will change direction at the front principal plane, P1. A secondary focal point, it changes direction at the back principal plane. Let's go back to that complex, crazy problem. So again, giving us front and back surfaces that we haven't addressed yet, but it's telling us the location of the front and back principal plane. So now I can add everything I know here to my diagram. So here I have an object, a green arrow. I've got a lens over here. I know the power on the front of the lens, the power on the back of the lens. I know the thickness of the lens is 3 centimeters. I've got a refractive index, and I know the exact location of the front principal plane and the back principal plane relative to that lens. So we knew that the object was 50 centimeters from the front of the lens, and then we have a 3 centimeter thick lens, and the front principal plane is 3.33 centimeters away from the front, and the back principal plane is 1.67 centimeters away from the back of that lens. So these are the exact locations of where all the action is going to happen. When it's all said and done, we're still going to use U plus D equal V. It's just we're no longer going to use the assumption version. We're going to use it thick lens style. And so now we're talking about the dioptric power not when it hits the front of the lens, as we've been doing, but the dioptric power when it reaches P1. So U is going to be the distance from that object to that front principal plane. And so we have to know that distance. And so we're told that the object is 50 centimeters from the lens. We're told the thickness of the lens. We're told the exact location of P1 relative to that lens. And so it was 3.33. So we have to add that back to 50, and that gives us the 53.33. And then, of course, we divide that into 100 to get our answer. So here it is diagrammatically. So U is not the object to the front of the lens. It's not 50 centimeters. If we're being exact, if we're accounting for lens thickness, then it's to the front principal plane. And so U is not 2. U is actually minus 1.875. What about the D? Well, D is the formula that you see here, and I know that that looks a little complicated, so we're going to walk through that. FD is not fire department. It is front dioptric power. BD is the back dioptric power, and you can see here lens thickness, refractive indices. Lens thickness has to be in meters. We've got that noted here, and then we multiply by the front dioptric power times the back dioptric power. So with D, we need all of these factors, and that's why you have to know the front, the back, the lens thickness, the refractive indices. So let's put that into our formula. Okay, so you put all of that in there, and then you work your order of operations, I think is what it was called. And you can see here as we walk down doing our basic mathematics, keep going, and D becomes 6 diopters. So it's getting a little more comfortable now. U plus D equal V. We have U and we have D. Let's put all that together. Now I can calculate V in the regular old way, 4.125 diopters. I can divide that into 100 and get 24.24 centimeters. But here's the question. 24.24 from where? Because in the past, in the simplified version, thin lens version, we said that it's just from the back of the lens, but now we have to account for every detail. And the basic idea is that P1 is all about the object, about U, and then P2 is all about the image. So it's not from the back of the lens, that 24.24, it's from P2 because that's where the action is happening. Let me show you that in a diagram. Just looking at V here, you can see P2 is 24.24 centimeters off to the right of P2, not 24 from the back of the lens. So here we are, 24.24 to the right of P2. That means that if we're going to use the back of the lens as a reference, it's actually 25.9 centimeters to the right of the back of the lens. Now, this next diagram I'm going to show you is incredibly busy, but bear with me. Here it is. Here's the final answer. Everything that we know. You can see right where that image is going. The rays start out parallel, they hit P2, and they go through that secondary focal point. And then the diagonal ray goes through the object through the primary focal point, and when it hits P1, comes out parallel. And where those two lines intersect, that is like drawing a central ray, isn't it? That's where the object is going to be. That's exactly where the object is going to be. It's going to be 25.9 centimeters from the back of the lens. So that is the thick lens style. Now, wouldn't it be fun to compare all of that work with the assumptions that we've made, the simplified version? Here we go. Thick lens style on the left, then on the right, and you can see the one answer gives you 25.9 centimeters to the right of the back of the lens, and the other simplified version gives you 25 centimeters to the right of the back of the lens. So you should be asking the following question. Do I care? Does 0.9 centimeters matter? So if we're talking 50 centimeters versus 50.9, it doesn't clinically matter, right? 2 diopters versus 1.96. You can't make a pair of glasses 1.96 diopters. However, if we're talking 4 centimeters versus 4.9, now we're talking 25 diopters versus 20.4 diopters, and that's a pretty large difference. So, and you can see down there at the bottom that 20 centimeters versus 20.9 is kind of halfway in the middle, but it starts to become clinically significant because now it's a quarter diopter difference, which we can prescribe a quarter diopter difference. So once again, remember back in the other lecture where we were talking about when we prescribe glasses and vertex distance, and if it's anything over 5 or 6 plus or minus, you really need to make sure that the vertex distance is correct for lens effectivity. It's the same deal here. It's like optics is all connected somehow. Weird, isn't it? So we were walking along in Carmel, California, and we came across this bakery, and I don't know what any of these things are called, but they look delicious, none of which was on my diet. I didn't get to try any of these, but if you ever do find these, please have them, eat them, enjoy them, and then I can live vicariously through you. Let's talk about optical center. So here we see a central ray drawn through the optical center, and again, it's assumed a thin lens. This is the simplified version, but like everything else, nothing is really that simple. In reality, these rays are going through what's called nodal points, and you can see here that the ray comes in diagonally from the object on the left. It hits the first nodal point. It then goes kind of completely horizontal till it hits that secondary focal point in which it comes out. So those are the nodal points. Why do we care about nodal points? Because they give us another ray as if we needed it, but they gave us another ray to help locate the image. So let's add that to our cardinal point diagram. If I didn't mention it, this is called a cardinal point diagram, and there are 6 cardinal points, and you can see them here. We've just added that one that goes to the nodal point 1, and then it goes horizontal and it exits nodal point 2, and the rest you've already seen, but you've got all of these points telling you where the image is going to be. Now, again, this is kind of a concept lecture, but let's take it a little bit further. How do we calculate the focal length of a lens? Well, that goes back to our first lecture, and the focal length was 1 over d, or we like to use centimeters, so it's 100 centimeters divided by the dioptric power of the lens. But what if we wanted to calculate the focal length of a thick lens? So a lens has 2 focal lengths, a primary and a secondary. And so the primary focal length is the distance from that primary focal point to the front principal plane. It's also, more interestingly, equal to the object media refractive index divided by the dioptric value. Why do we care about that? Because that's how we get that inverse relationship between the focal length of a lens and the dioptric value that we've been talking about, again, since first lesson. And the reason that it's 1 over d is because it's in the air, and air has a refractive index of 1. If we put it in a tub of water, then the focal length is going to be 1.33 divided by the dioptric value. So let's put some real numbers to this. Let's take a 20 diopter lens. What's the focal length of a 20 diopter lens? It's 100 divided by 20, so 5 centimeters. But put that 20 diopter lens inside the eye in the aqueous, and it now has a primary focal length of 6.65 centimeters. Why do we care? I'm going to get to that, but let me tell you one thing first. And that is that although we're talking about the primary focal lengths in that example, it's true also for the secondary focal length. I just wanted to get that point in, that the distance from the back principal plane to the secondary focal point is the other focal length of that lens, and the other formula also holds. Now, on to some clinical relevance of all this information. So here we go. We have a cornea with the central corneal thickness shown here, 42 diopters on the front, -5 on the back, and magically, somehow we know that the front principal plane of this cornea is located 1 centimeter behind the cornea, and what we want to know is, where is that primary focal point? So here's what you need to know. The refractive index of the cornea is truly 1.376. We're not going to use a fudge factor here. The front of the cornea is in air, so refractive index of 1, and behind it is aqueous, 1.33, and we've got our formula right here. We need to know the dioptric power of the cornea. Using the information that they've given us, shown here, we can do the following calculation and come up with something that looks a whole lot like a K reading, 37.084. So in this example, the primary focal length, which once again is the distance from the primary focal point to the front principal plane, that is 1 divided by the 37.084 that we found by calculating D. And that tells us that it's 2.7 centimeters away, but if we're measuring it from the front of the eye, it's 1.7 centimeters because we said that that front principal plane is 1 millimeter inside of the eye. Now, remember that number 1.7 centimeters, because here's where this becomes important. Knapp's law tells us that the retina image size doesn't change if the secondary nodal point of the glasses is placed on the primary focal point of the eye, at least for refractive errors that are axial in nature. What does any of that mean? Well, it has to do with aniseikonia. Aniseikonia means image size difference, and that occurs when we give someone a pair of glasses that are different by a significant degree. For most people, they can tolerate a difference of up to 6%. In diopter terms, that usually means 3 diopters for standard vertex distance kind of stuff. So let me give you an example. If I gave you a pair of glasses and you're -1 over the right eye and you're -10 over the left eye, you're probably not going to like me very much because your brain's not going to be able to put those two images together. Why? Because minus lenses give us minification. And the right eye would be minified by just a little, but the left eye would be minified by a whole lot. So you would be seeing one image much larger than the other. Your brain will not be able to fuse that for most people. So when you're prescribing glasses, kind of keep that in mind, that you don't want the eyes to be different by more than about 3 diopters for most people. Now again, this is for adults. This has nothing to do with kids. Kids are very adaptable, and we're not talking about them at all. So for adults, about 3 diopters in general. However, there's an exception to this, which is Knapp's law. Knapp's law once again says that if I make my vertex distance 17 millimeters, in other words, if I put that lens on the primary focal point of the eye, at least when that myopia or hyperopia is because the eye is too long or too short, then no aniseikonia will occur no matter how different those two lenses are between the eyes. So that is the clinical relevance of knowing all of that thick lens stuff. This is the one clinical thing that you probably could have easily understood without this whole lecture. But, you want clinical relevance when you're teaching optics, and bam, there it is. Here's something that is of not just historic interest, but some practical value. It's a classic question: what level of vision do we need to read the average newspaper font? And this is not on your phone or tablet where you can make it bigger. This is the actual newspapers that, some people still read. Way back in the 1800s, Kestenbaum figured out that if you took the Snellen visual acuity and you flipped it upside down, you could figure out the ad that you needed to read the newspaper. In other words, if I measured you at a vision of 20/40 and I flip that upside down so that it's 40/20, 40 divided by 20 is 2. And so you would need a +2 to read the newspaper. Now, it's assuming there's no accommodation, but in these cases, and let me tell you, there's no accommodation. Another example, if I have a vision of 20/100, I flip that upside down, and 100 divided by 20 is +5 is the ad that they would need. This is the bifocal ad to read the newspaper. And here it is, the classic question that we've just gone through, +5 to read J5, which is the small articles in newspapers classically. That is the classic question that you will likely encounter at some point in your life. So here's a new classic question. Patient has the best corrected visual acuity you see here, and what ad does she need if she has to read J1, so smaller than J5? So Kestenbaum didn't really tell us that. I mean, if you take 60 over 20 and you get +3, that's for J5. That's not J1. And so that leads us on our quest to find Kestenbaum's lost rules, because it turns out that if you read his paper from the 1800s, which is a really great paper, it's kind of fun to read if you can find a copy, he gave us 3 formulas, not just one. And I know that you're dying to know what those other 2 formulas are, and I'm not going to string this out. I'm going to tell you. So let's go ahead and reveal the lost rules that have not really actually been lost to history. So here's Kestenbaum's first lost rule. We had a patient with 20/60 vision. She had a reciprocal value of 3, but we can't just use 3. That's the J5. So if we want her to read J1, the formula is 2.8 times RV. And in this instance, RV does not stand for recreational vehicle. It stands for reciprocal vision. So 2.8 times that 3 is 8.5 that you have to put into her bifocals to allow her at 20/60 vision to read J1. Can you imagine how heavy plus 8.5 ad would make your pair of glasses? And I promised you that he gave us 3 rules, and the third one was, what do you need to see J3? And it's 1.4 times that reciprocal vision or reciprocal value or the flipped Snellen acuity, whatever you want to call it. So you'll hear quite a bit about Kestenbaum's rule, but remember, it was rules plural. And here they are, whether you want to see J1 through J5. Hey, thank you again for joining me for this lecture. I've enjoyed talking with you. Next up is our final talk. I know it was quick. It felt quick to me. And we're going to talk about some mirrors. So please come back and see me for that final one, and we'll reflect about mirrors. Have a good day.